Okay, I'll start anyway. I gave you Noether's theorem, but I have to admit I was confused by all the confusing descriptions that I noticed in all the textbooks. And I'd like you to correct the notes to just delete this stuff about the equations of motion. This is implied by the first statement. So we have an action. It's a function of QA. We have a transformation, QA going to Q prime A. And if that transformation leaves the action unchanged up to surface terms, okay, in other words, if S prime equals S, so under the transformation Q to Q prime, which is Q plus delta Q, if S prime equals S plus surface terms, okay, then it follows that the equation of motion for Q imply the equations of motion for Q prime. Okay, because these two actions are equivalent up to surface terms, and when you vary an action, you require that the the variation be zero independently of the surface terms, and that's what gives you the equations of motion in between the two time boundaries. So that's sufficient for Nurse's theorem. And in fact, one should emphasize that this is a symmetry of the action. We could, in fact, add this up here, independent of the equations of motion. Let's see, which holds even which holds without using the equations of motion. So there's a nice mantra, which I guess David told me, which is that off-shell symmetries. Off-shell means that you have some transformation that does not use the equations of motion. And it even holds in, for example, inside the path integral for all paths. Doesn't matter about the classical equations. So off-shell symmetries give on-shell conservation laws. Noether's theorem gives you a conservation law which holds if the equations of motion are satisfied. So that's a kind of nice mantra, off-shell symmetries. And what I mean by an off-shell symmetry is a transformation which leaves the action unchanged up to surface terms. Off-shell symmetries give on-shell conservation laws. And on-shell means using the equations of motion. Okay, so we're going to do some examples, which hopefully will make all of this very clear. So this is the free relativistic particle. The action, as we've discussed, is m naught c squared integral dt square root 1 minus dx dt squared over c squared. Okay, so as we already discussed, this is Lorentz invariant, this action, because it involves square root of dt squared minus of c squared dt squared minus dx squared. For small velocities, when this dx dt over c is less than 1, this becomes approximately minus m naught c squared integral dt. And then expanding the square root, the two minus signs cancel, and I get plus integral dt 1/2 m naught dx dt squared plus order v fourth over, plus dot, dot, dot. Corrections which are small, down by v squared over c squared. So this is the familiar term from Newtonian mechanics. And this term, you can ask, what does it represent? Well, of course, it's just a constant, so it doesn't contribute to the equations of motion at all. But it's minus. And if you remember the classical, the action in classical mechanics is kinetic minus potential. So that suggests there's a potential energy of m naught c squared. Okay, so you can directly read off that it looks like there's a potential energy m naught c squared. But now we're going to derive this absolutely properly, and that's using Noether's theorem. So we're going to start from this action and just derive the corresponding conserved quantities. So this leads to conserved quantities. So first of all, consider the simplest symmetry of this action, which is spatial translation. Okay, so x of t goes to x prime of t, which is equal to x of t plus epsilon, where epsilon is any 3-vector, constant 3-vector, independent of time. Now, obviously, that leaves the action invariant because dx dt, there's no contribution to dx dt. So when I take the s prime, all I'm going to do is s prime is the same expression, but x of t gets replaced by x prime of t. X prime of t is this guy, and then d by dt of epsilon gives 0, so it's obviously unchanged. There's no surface term or anything. The action is completely invariant. So here comes the clever idea. By the way, this is only true. It's a symmetry only if epsilon is constant, right? A symmetry if epsilon is constant, independent of t. And that's the definition of a continuous symmetry, okay, which when I gave you Noether's theorem, I said definition of a continuous symmetry is some transformation which has some parameters in it, and if those parameters are constant, the action is unchanged up to surface terms. Okay, clever idea is to say, what if we take epsilon to be a function of t? So Noether, let epsilon be a function of t. Then delta s, the variation in the action, so that's s prime minus s. Now, the only thing that's going to change is this term, right? And so what I need to do is calculate the variation of dx dt. The variation of delta x dt, what does that define to be? Well, that's equal to dx prime dt minus dx dt. Okay, that's the definition of the variation. And dx prime dt minus dx dt, all I'm going to get is that epsilon is going to be d epsilon dt. It's a vector, 3-vector. Okay? So now when I vary the action, I've got to vary dx dt. So what I'm going to get is minus m naught c squared integral dt. I'm going to vary this guy with respect to dx dt. Okay, so now we use the chain rule that I vary this. I'm going to get in the numerator dx dt d delta x dt over c squared. I'll get a factor of 2 because it's dx dt squared. But I've also got a factor of 1/2 from the square root. So I'm going to divide by the square root. 1 minus dx dt squared over c squared. And of course, I get a minus sign because differentiating this will give me a minus sign, so it cancels that minus sign. Okay? And so what I've got here is, notice the c squareds cancel, so I've got m naught integral dt, and then dx dt, and then I've got epsilon d epsilon dt, and then I divide by the square root. Okay, and that's exactly what Noether argument. The Noether argument envisaged, which is that the action variation must be 0 if epsilon is a constant. So when you vary it with epsilon not a constant, it's going to be proportional to the epsilon dt. The other possibility is epsilon of t times d by dt of something, which would, when integrated, give a surface terms. Okay, they don't arise here. Okay, so by the Noether argument, delta S equals 0 on shell, right? i.e., using the equations of motion. Why? Because this variation of x is a legitimate variation, and the variation of the action should be 0 for all variations using the equations of motion. And so what I can do is integrate by parts. So I get equals minus using, this should be for arbitrary epsilon of t. So I can integrate by parts. I get m naught integral dt d by dt of dx dt over square root 1 minus dx dt over c squared multiplied by epsilon of t. Okay, so that quantity has to be 0 for arbitrary epsilon of t. And that means that the integrand, that this function has to be 0. So d by dt of dx dt over the square root must be 0. Okay, and in fact, let's put the m naught in here. And this implies that the conserved, so p, which is m naught dx dt over root 1 minus dx dt squared over c squared is conserved. And of course, that's the momentum. Okay? Now, it's a little bit trivial. For a free particle, dx dt is a constant anyway. It's going in a straight line. Okay, so everything's constant. But the point of this derivation is that when I couple this particle to other things, such that the whole combination is translation invariant, okay? And then I try to derive the total momentum of everything, right? This will be the contribution of the particle. And so the particle's momentum, the field's momentum, the other particle's momenta, all of those together will be conserved. Okay, so that's how you get momenta. And in fact, the definition of momentum, it's the Noether quantity which corresponds to spatial translations. That's the definition of momentum. Yeah?
So you kept saying up to surface terms.
Right.
I was wondering what the surface term is that we're
0.
ignoring.
It happens to be 0 for this transformation. I'm about to do one where it's non-zero. Okay? And this is kind of where a lot of the textbooks go wrong, is that they don't state this clearly. Okay. So now let's consider, so that was spatial translations. Okay? Energy is a quantity which exists because of time translation symmetry. Okay, so now consider symmetry under time translations. And so what that means is that x of t goes to x prime of t, which is x of t plus epsilon, which to first order in epsilon is x of t plus epsilon dx dt. Okay, so in the notation I gave in the earlier, epsilon is the parameter of the transformation, and the dx dt is the generator of the transformation. Okay, it's the velocity of the particle. So we're changing the coordinates, the trajectory of the particle, by a term proportional to its velocity. And there is no preferred origin of t, so this can't possibly make any difference to anything. There's no explicit time dependence in the action, in the equations of motion. So if I shift time by a constant, it can't possibly make any difference. So this must be a symmetry of the system. So let's see what happens to delta x, to delta s. So delta s, in this case, we have got to vary the original expression. So I'll do the same calculation. This is still valid. So it's m naught c squared. Let me just compute the change. So we say delta x of t is epsilon dx dt, right? And what is delta dx dt? Okay. Well, these derivatives commute. They're partial derivatives. I mean, one is a time derivative. This is a variational derivative. They still commute. You can check that. Just take the definition of delta x as being x of as being this version. So these things commute. So this is equal to d by dt of delta x. And delta x is this. And so this is equal to, now, if I allow epsilon to be a function of t, that's what I'm told to do in the Noether definition. Epsilon should be a function of t. This gives me epsilon dot dx dt. Well, let's write it out. d epsilon dt, right? Plus epsilon d2x dt squared. So now when I do the variation of the action, what I'm going to get is all of that stuff. Integral dt. Then I'm going to get dx dt 1 over c squared 1 over the square root. And now it's all going to be multiplied by the variation of dx dt, which is d epsilon dt times, well, you know what I'm going to do? I'm going to write it this way. I'm going to write it as d by dt of epsilon dx dt. Okay, because this is the variation delta x. Okay, and now Noether tells me to let epsilon remain a function of time. Let epsilon be a function of time. And so what are, let me try and compactify the notation just so that it is easier to read. Integral dt, I can cancel the 1 over c squared. So this is going to be x dot over root 1 minus x dot squared over c squared. And then in the numerator, I've got epsilon dot x dot plus epsilon x double dot okay, just calculating this out. And now what you notice, well, the first term is good, like I had before. It's something which would vanish if epsilon is a constant, but involves epsilon dot. The second term, notice the coefficient of epsilon here is, total derivative, right? Because it's d by dt of the square root. It'll give me this x double dot. So this is equal to m naught integral dt x dot over the square root times, well, let's write it this way, x dot squared times epsilon over the square root. That's the first term. And the second term, I can integrate by parts minus, this is not a vector, sorry, that's a, this is a dot product, and this is epsilon is a scalar quantity. Minus, so here I'm integrating by parts.
Should there be a square dot?
Sorry?
In the first term, epsilon dot.
Thanks. Epsilon dot. Sorry, the second term, I'm not integrating by parts. I'm just writing this as a derivative. Epsilon d by dt of, that should have a minus sign, minus epsilon d by dt of the square root of 1 minus x dot squared over c squared. Let's just pick that up. Okay, because if I differentiate this thing, I get x double dot, I probably need a c squared in there. I surely need a c squared here. C squared. Yeah, that's good, because now the dimensions are right. Okay, that's a velocity squared, that's epsilon dot. Velocity squared, epsilon d by dt is the same dimensions as epsilon dot. Everything else is dimensionless. And so now I have the second type of contribution I mentioned in Noether's theorem. It's something which, when epsilon is constant, just gives surface terms. The variation of the action gives surface term, because this is an integral of a divergence, so it just gives the two limits, the quantity at the two limits of the integral. Okay, so what does Noether tell me to do? Well, Noether says integrate by parts on this epsilon, and then argue that the coefficient of epsilon must be 0, because this must be 0 for all epsilon. Okay, so this is equal to minus m naught. I'm going to integrate the first thing by parts. So epsilon of t, d by dt. Here I'm integrating by parts, so I've got x dot squared over square root 1 minus x dot squared over c squared. And in the second term, have the minus sign already. So plus c squared. The epsilon I pull out. This is square root 1 minus x dot squared over c squared, close bracket. Okay? And this has to be 0 for arbitrary epsilon. Therefore, d by dt of this must be 0. But what is that? Move it up so you can see it. That is which board? The rear board. We can combine these terms. Okay, just multiply the square root. This square root times that square root is 1 minus x dot squared over c squared. So the minus x dot squared cancels. So this whole thing is just c squared over root 1 minus x dot squared over c squared. Okay, so it follows. So this equals 0 for all epsilon of t. So it follows that d by dt of m naught c squared over square root 1 minus x dot squared over c squared equals 0. Okay, and what is that quantity? Well, that quantity is just gamma m naught c squared is conserved. And this is the energy of the particle. Okay? And as I explained, for a free particle, the x dt is a constant in the equations of motion, so this is not very useful. But when you have a collection of particles and forces, and the whole system is invariant under time translations, this expression is the energy of the particle. And even if it exchanges energy with other particles, there will be a total energy which is conserved. Okay, so this is the best derivation of E equals mc squared. Okay, because the E is the energy, it's a conserved quantity corresponding to time translations, and we just calculated it, and it's mc squared. Yeah.
Is there any way to rewrite the action in like a manifestly covariant form so that you can derive the energy momentum or vector in one go?
Yeah, there's a subtlety, which is that when you talk about Noether's theorem, it involves time. That the action is a time integral. You've got to choose a time. You can choose any time using a Lorentz transformation, but you better choose one of them. Okay? As soon as you chose that time defines the energy. Okay? So it's the energy in that coordinate system where that time is the time. Okay? So if you try to define an energy for all times at once, it doesn't actually mean anything, because it's the energy varies according to which time you use.
Could you choose proper time?
No, because if you, let me think about that. Proper time is invariant. Energy is not invariant. So there's no way you can use an invariant thing to derive a non-invariant thing. No. So a similar issue arises when you consider Lorentz transformations, because some of them are rotations. Like rotations only mix the axes, the spatial axes. Okay, so those are fine. The others of them are boosts. They mix x and t. And those boosts are going to change the time. And they do not satisfy Noether's theorem. The change in the action induced by a boost is not of this form. And therefore, there is no conservation law corresponding to boosts. So those Lorentz transformations mixing space and time do not yield conservation laws. The rotations yield angular momentum, which is conserved. So it's very important that there's a distinction between time and space. In the action formalism, the action is an integral over time. And that distinction is important in the definition of energy. Yeah.
I've forgotten why it's physically reasonable to elevate epsilon to time dependence?
It's not physically reasonable. It's a mathematical trick. Noether's argument was that if you've got a symmetry, which means some transformation when epsilon is a constant, you consider mathematically a variation which corresponds to making epsilon a function of time. And then the argument is that the variation of the action must vanish around a solution to the equations of motion for any variation. So that variation with epsilon being a function of time is a legitimate variation, and for such a variation, delta S must be 0. And when you work out the consequences of delta S being 0, where in the case where epsilon is a function of time, you find a non-trivial conservation law. That's the idea. Okay, so these are examples, and it's sort of a funny thing that if you look in the textbooks at the derivation, the best discussion of Noether's theorem I found is in Weinberg's book on quantum field theory, at around about the middle somewhere, buried in the middle. He doesn't even mention it in his book on general relativity. He doesn't mention Noether's theorem, no reference to it. Like the most important foundational result in 20th century mathematical physics. Doesn't mention it, but he does give a good discussion in his quantum field theory book. But even his discussion means that the conservation of energy is a special case, which is mentioned at the end. It's a funny thing. So the versions of Noether theorem that he gives sort of get progressively more complicated, and energy is the most complicated. And I think that's not right. Yeah.
I'm just curious, do you know where E equals mc squared came from originally?
Einstein.
Oh, yeah, no, so I know that, but I mean, did he try to formulate an action principle and then?
No. Einstein had an argument which you will do in today's tutorial. Einstein had an argument which basically, as you'll see, says, consider I have some object of mass m, like an atom. And then, everything comes from electrodynamics in relativity. The whole of relativity just came from electrodynamics. Einstein would be the first to say, I owe it all to Maxwell. Okay? So Einstein said, imagine we've got a particle that emits some radiation. So it's emitting energy. We know radiation carries energy. So we know that the energy of the particle has to change. Okay? There's some energy in the radiation. And then he gave this wonderful, clever argument that if you have Lorentz invariance and energy conservation, it follows that, you see, he knew that this carries an energy E, and he knew that the momentum of the photon, we call the photons gammas, the momentum of the photon, he knew from, I've already derived this, is E over C. Okay, so this idea of photons was in the air because he had just explained the photoelectric effect with photons. And he knew that for photons, their momentum must be there. And by this I mean the magnitude of their spatial momentum. He knew that the magnitude of the spatial momentum was the energy over c. Okay, so it turns out that this equation plus energy and momentum conservation plus Lorentz invariance is enough to imply that m minus m equals 2 times the energy of the photon over c squared. So the change in the mass of the object is the energy of the photon over c squared. That was the formula he derived in 1905 in this paper of 3 pages with no references. And if you take this formula and you just say, so there are 2 photons here because you can use momentum conservation most easily if the photons are going in the opposite direction. Then it's clear that this particle is at rest, has no kinetic energy in this frame. So basically what he's saying is that the change in the mass of a particle was the energy emitted over c squared. And so now you can imagine that the particle just decayed completely, just lost all of its mass into radiation. Well, then all of its mass goes into energy of the radiation, and by this formula. So that gives you equals mc squared. So that was Einstein's argument. You know, Noether's theorem wasn't even known in 1905, so he couldn't have done it this way. Any other questions? Yeah.
So you say that there is no conservation law associated with boosts?
Yeah.
And why is that?
Because they involve the time. Boosts are not a transformation alone of the coordinates of the particle to the coordinates or to the velocities. They actually involve the time explicitly. So I just invite you to do this calculation for boosts. Okay, and what you will find is that the action is not invariant even if epsilon is a constant. Because what will happen is that the t will come in, and then the action just won't be the same. Yeah?
Can we also argue that boosts aren't proper symmetry in and of themselves because they don't close to boosts, they close to rotations? I mean,
that you could... no, I don't think so. I don't think you can argue that. Boosts are a legitimate infinitesimal symmetry. That's all that's required. It doesn't matter about the closure. All that matters for Noether's theorem is the infinitesimal symmetry. Okay, so now we're going to see how the action principle in a certain sense, gives electromagnetism and gravity for free. Okay, this same action principle, the action principle for the particle, okay, so it's a slight exaggeration, but it's not much of an exaggeration. The statement is that if all I knew was the action for a relativistic particle, i.e. the length of the world line, and I understood all this, and then I ask, what could that particle possibly couple to? What forces could it couple to? As soon as you ask that question, you basically get electromagnetism and gravity. Okay, so let's see how that works. So the action for a relativistic particle is the length of the world line times minus m. Now let me get these units right. Yes, minus mc square root minus eta mu nu dx mu dx nu. Okay, so if you remember, this guy is going to basically give us c squared dt squared. And when I take the square root, I'm going to get c dt, so I'm going to get minus mc squared integral dt, and the rest of the stuff in the square root will give the square root. So that was the action for a particle, and basically the definition of its mass is the coefficient of the length of the world line. Okay, so that's the action for the free particle. So now you say, I'd like to couple this particle to a force, to something else. What can I do? Now, I want to maintain Lorentz symmetry. I want to keep the whole theory symmetric under Lorentz transformations. So how can I couple? The particle is following some curve, right? X mu of lambda. A little piece of this curve is dx mu. And this integral represents adding up all the dx, all the lengths of those little pieces of the curve. What am I going to couple this dx mu to represent a force on the particle? It's basically, there's only one thing you could do, or at least there's the simplest thing you could possibly do. What could I do? So I want to couple dx mu. I'm going to have an arbitrary coefficient, so I'll call that the electric charge. What?
Any vector field.
Any vector field. So let's call it a mu. Okay, so a mu is going to be a function of the x's. So I'll often use this notation where what I mean here is this is a vector which depends on space-time coordinates. And I'll kind of leave off the indices when they're inside the argument. Otherwise, you might get confused. So this vector has an index, but it depends on t, x, y, z. And I'll just use that so without an index. So this immediately implies that if we want forces between our particles, we're going to need something else. Okay? We'll call it a mu. As soon as you say that, you think, well, maybe this has something to do with electromagnetism. Okay? And indeed it does. It turns out that it is exactly the vector potential for electromagnetism. So once I have the same mu, I can, of course, construct a symmetric tensor, antisymmetric tensor, just by differentiating it. And this is the correct coupling. So a mu is the electromagnetic vector potential. Okay, so electromagnetic forces really are the simplest thing you could possibly invent that couple particles, that represent forces on particles. So that's obviously Lorentz invariant. And let's just check this. So it should be true that when I vary this action, I get the Lorentz force equation, right? And so let's vary it. So delta S is equal to, and now we've got to do, I'm going to leave off this m naught, the naught index. That m is the rest mass. Okay, so this is going to be mc. We do our usual variation of the square root. We get 1 over the square root. And then we vary this guy in the numerator. The two minus signs cancel. The factor of 2 cancels with the half from the square root. And so we get dx mu delta, d delta x mu. Okay, so I'm just varying. X mu goes to x mu plus delta x mu. The variation of the action looks like this. And then I've got Q. Let me first vary the, okay, so I'll write it this way. D delta x mu, yes, d delta x mu times a mu plus q dx mu. And then the variation of a mu is a mu comma nu. So a mu is a function of space-time coordinates. So when I vary it, what I need to do is vary the space-time coordinates of the particle. You see, this x here is the x mu of the particle. I mean, it's the position of the particle. That's how the action is defined. So when I vary x, I've got to vary the argument of the vector potential. Okay, so this now becomes a mu of x plus delta x. Expand to first order in delta x, and I get this expression, d nu delta x. Delta x, sorry, that's wrong. Delta x nu Sorry, that's it. There's no D. Okay. Delta x mu. Okay, so I'm just varying that vector potential. Sorry, there's another term. I've just forgotten the argument for it. Yes. That's fine. That's right. Yeah, sorry. This is all correct. So now I haven't put any time in here, right? I've just done this as delta x. Okay, let's now, we want to get an equation of motion for the particle. That's going to involve the proper time. So I need to rewrite this in terms of proper time. So what I'm going to do is insert d tau over tau. Yeah, so let me do it this way. Insert this factor. Yes. Actually, just use this fact. So multiply this by d tau and divide by d tau. Okay? So what's the point of that? Well, this is now dx mu d tau. I'll leave that d tau outside. This is now d delta x mu by d tau. And in this expression, I've got dx mu d tau over there. And of course, this square root is d tau. Okay, so this whole term here is mc dx mu d tau d delta x mu d tau. Right? Now I can do my usual things about integrating by parts. So now integrate by parts. And what I'm going to get is equal to integral minus, integrating this guy by parts, I get delta x mu times d2 by d tau squared, mc dx, well, I put I've kind of, one of these indices should be down. Let's put that one down.
Excuse me?
Yeah.
Should there be eta in the first term, something contracting the indices of
Sorry.
the last equation?
Sorry, let me just finish writing that. Say it again.
Sure. I'm just confused about the three indices in the first term.
Yeah,
Will there be an eta contracting a mu?
they should. So you can just put one of them down.
Okay.
Okay. Yeah. So the x mu d tau d delta x nu eta mu nu is, of course, equal to the x mu d tau d delta x mu. Okay, so all the eta does is lower an index. Okay, so the first term is this, because I just integrated by parts. I got a minus sign, and I have d2 by d tau. Oh, sorry, this is like that. In fact, let me just simplify it. If m is independent of tau, this is just going to give mc d2x mu d tau squared. Okay, and remember, eta is just a constant matrix, so you can have the indices this way or that way. It doesn't matter as long as they're contracted. So that's the first term. And then the second term, I've also got to integrate by parts. So now I get minus q delta x mu, right? And then what is dA mu by d tau? dA mu, remember A mu depends on x. So let's write it this way. d by d tau of A mu of x. Now what the hell is that x? Well, the x is x of tau. It's the position of the particle, right? When I wrote down this action, implicitly that x there is the position the particle is located at. That's the only position I know about. Okay, so this x is actually x of tau, the position of the particle. So the derivative of A mu of x of tau means partial derivative with respect to its argument, okay, multiplied by dx nu d tau. Okay, so A mu is a function of x of tau. So when I differentiate, I use the chain rule. I first differentiate with respect to the argument, then I differentiate the argument with respect to tau. Okay, good. So in this term, we've got d nu A mu dx nu d tau. So that's the second term. This term already is in a coefficient of delta x. So basically I have plus, try and write it the same way, delta x mu. So I'm going to relabel these indices, nu as mu and mu as nu, to make it more similar to the first two terms. So delta x mu, A nu, comma mu, there's a q, dx nu d tau. Okay? So we're going to set this equal to 0 for all delta x 0, for all delta x mu of tau. And so this gives us the coefficient of delta x mu must be 0. So it means that mc d2x mu d tau squared. I'm going to actually raise this one and lower that one. Okay, is equal to q, and then d mu A nu, and then from this term minus d nu A mu times dx nu d tau. And of course, that's equal to q f mu nu dx nu d tau. Lorentz. Okay, so all of that is built into the free particle action. Now, actually, a lot more is built into the free particle action. This coupling, this Q A mu coupling, is an amazing thing. In electrodynamics, people in the 19th century at least, and in fact for most of the 20th century, people thought that the A mu was just a mathematical guy. That the A mu, the vector potential, was just a useful thing that you'd use to solve Maxwell's equations. For example, the electrostatic potential. That's often a useful concept in solving electrostatic problems. So they thought A mu was just a mathematical thing. But now you see A mu is actually the thing that comes into the action. And when you do quantum mechanics, what you do is you take this classical action and you consider this. Okay, so all of quantum mechanics is got from the, at least for particles and fields, is got from the classical action just by exponentiating it and then doing this path integral. Okay, the integral over all paths. So this is Feynman's, Dirac and Feynman's formula for quantum mechanical amplitudes. And so what you notice is a couple of things. First of all, the action has to have the same units as h bar in order for anything to make sense. And all the actions we have the units of h bar. Secondly, you'll notice there's a phase here. So the phase of s over h bar, and that's equal to, if I take that second term in the action, that will be q over h bar integral a mu dx mu. Okay, that phase in quantum mechanics can be interference phase. When I follow a particle along a path, it's going to the wave function. This is the formula for the wave function. Okay, the wave function can pick up a phase given by that path integral. Just comes straight out of the action. And a lot of time, people thought initially you can't observe the phase of the wave function. Then they realized that if you have two particles, and if you have a magnetic flux, for example, in a tube, and one particle goes one way and the other particle goes the other way, they'll have a different phase. Okay? And that phase will cause the two parts of the wave function to interfere. And so what it means is that even in regions of space where there is zero electromagnetic field, where this guy is strictly zero, if I take one particle through such a region, another particle through another region, and I interfere them, I'll see the effect. That's called the Aharonov-Bohm phase. Okay, and Yakir Aharonov is one of our visiting research chairs. I hope you'll get to meet him. You'll probably visit.
You already have.
Oh, you have? Good. So, yeah, so he's one of the kind of greats of 20th century physics. And he realized this when he was not so different age from you. Okay, that everybody had missed the fact that the phase is really matters. Okay, and it all comes out of this action. So this, in fact, was part of my reason for being a little pedantic and including all the C's and the mu naughts and the epsilon naught is, in the end, this should connect to real predictions and experiments. And I don't want this just to be, most of this course is kind of mathematical in flavor, but it's good to be able to convert into real numbers. That's why I put all the C's in and everything. There are other reasons too, but that's the main one. Okay, so there we have it. Now let me see. I'm not sure. Having said that, I'm not sure I got the C's all right. Let me.
I think yesterday you defined the detail to be.
Sorry?
I think yesterday you defined the target to have the unit of t, then that C shouldn't be there.
Say that again?
The last equation.
Yes.
C shouldn't be there.
This C should not be there. Let's just.
Left is MA, the other side.
X has dimensions of. Yeah, that's right. MA.
And the other
Electric field. Okay, so this. Yeah, we can check. Yeah, I think you're right, because this field strength, for example, goes like electric field over C. Okay, but this guy, yeah. How is it going to work?
No, that's derivation is under assumption.
XDT. No, that's.
D tau square is defined to be the unit of.
Oh yeah, sorry, I made a mistake here. This guy is not T. Sorry, It's CDT. Thank you. Okay, so that's gone?
Yep.
There we go. Thank you. That's gone. That's gone. And then I think we managed to get this correct somehow. Okay. Let me be satisfied with finding one factor of C. Okay. All right. So having done that, let us now also consider the, just as a side remark, this is the action for the particle. We'd also like the action for electromagnetism. In fact, the action for electromagnetic fields is, and so here we have an integral over all of space-time, d4x. That, as I discussed before, this d4x is really Lorentz invariant because I can write it as epsilon mu nu rho lambda dx mu dx nu dx rho dx lambda, which is obviously Lorentz invariant. That's dt, dx, dy, dz. Oh, it's proportional to that anyway. There's a factor of 12 or something proportional to this. So d4x times minus 1 over 4 mu naught f mu nu f mu nu. And then we have to put the current in, J mu A mu. And you can check that for f mu nu equals d mu a nu minus d nu a mu. Okay, so that's what the f mu nu here means. F is this expression in terms of the a's. And then if I calculate vary s with respect to a mu, and what we get is Maxwell's equations. D mu f mu nu equals minus mu naught j nu. Okay, so I'll just leave that for you to play with. The j mu for a particle, j mu for a charged particle, j mu is proportional to q dx mu d tau. And you can read more about that in any of the textbooks. I'm not going to dwell on it. There has to actually be a delta function of in space-time because the current is only non-zero at the particle. But I'm not going to go into that. Yeah.
I don't understand your claim about the invariance of d4x, the measure.
Yeah.
You have epsilon, which is totally anti-symmetric,
Correct.
multiplied by something totally symmetric. So I guess it should be 0.
No, why is this symmetric? This is not symmetric. This is a tensor.
Oh, right.
This is not a symmetric tensor.
Sorry.
Yeah, this. If I think about this as a matrix, it's dt squared, dx squared, dx dt. It's well, sorry, what am I doing? Now it looks symmetric. Yeah, hang on. Let me think. No, I'm getting confused myself. Yeah, you've got me confused too.
Isn't that shorthand for having wedge products between each one of the components? Because we don't really integrate over
yes, let me just think. It is shorthand for that. Let me think about that. It's a good point.
And that becomes like determinant G times the wedge product between just 0, 1, dx0, dx1, dx2, dx. That's what
Yeah, no, that's true.
So it's anti-symmetric and that is anti-symmetric.
Let me think about that. Okay, it's a good point. Any other questions? Yeah.
So if you write down the electromagnetic field Lagrangian, are you saying that if you take J and treat it as another degree of freedom, then you can back out the Lorentz force law?
If I
Something like that.
no, I'm not. Sorry, not saying. No, I'm saying if J mu is fixed. So this guy is contributed by the particles. Okay. So J mu you should think about as the current of particles traveling in space-time. Has nothing to do with the A. The J is the source for A. So when I vary this action, I just vary it with respect to the A.
I guess I was asking, could you also use that to get Lorentz force law by considering J somehow as another?
You can. If you remember, there is a conservation law. The Maxwell equations imply that the current must be conserved. In fact, that's not enough to get the Lorentz force law. But if you work out the energy in the particle, the energy momentum in the particle, and the energy momentum in the electromagnetic field, and if you require the total energy momentum is conserved, that gives you the Lorentz force law. I think Gang was going to put that in.
I think that's in the tutorial.
That's in the tutorial.
Work out the energy momentum of the particles.
Yeah. If you demand the total energy momentum is conserved, it also gives the Lorentz force law. Okay, any other questions? Yes.
What are we taking as the endpoints for that action integral?
Sorry?
What are we taking as the endpoints for the integral of like d4?
This integral? Or this one?
The field.
Oh, so the idea here is just ignore surface terms. Don't talk about it. Okay.
Take them to infinity.
Yeah, so one way of saying it is if we consider fields which vanish sufficiently rapidly at infinity, and we consider variations of the fields which also vanish, well, either is enough, in fact. So if I consider fields and I consider variations of the fields, delta A mu, which vanish at infinity, and I insist the action is doesn't vary for any variation, then I can ignore the surface terms.
And that's valid because like Coulomb law decays?
It's a delicate question whether it's valid. Okay, yes.
I may want why that's a little confusing, because here like happened kind of smooth transition from point theory to field theory.
It's not really a smooth transition. The point particle was only defined by this trajectory x mu. Okay, so the treatment of the point particle is completely local to this curve,
Yes.
whereas the A mu is
Yes.
propagating out here.
Yes, but here we treated time and space as totally different things.
In Noether,
Yeah.
yes,
And over there we're like
they're all
integrating
together.
over a whole space.
That's right. That's right.
Space touch.
That's right. So I haven't really talked about the derivation of the stress-energy tensor. We'll come to that later. The best derivation of the stress-energy tensor, in fact, involves gravity. Okay? And we haven't even talked about gravity. So I could give you Noether's derivation of the stress-energy tensor. The trouble is it sort of doesn't work for electromagnetism because it ends up, if you use Noether's way of doing it, you end up with a stress tensor which is not symmetric under mu and nu. And if you look in the textbooks, there are pages and pages of excuses why I get to add back surface terms and blah, blah, blah to get a stress tensor. But if you just go to gravity and you consider Minkowski space as a special case, then you get a stress tensor in one line. And so I deliberately avoided all this complication. Okay. Okay, so I want to emphasize one other thing. I claimed up there that we get electromagnetism and gravity for free. Why do I get gravity for free? Well, the point is, when I look at that action, the first term there's this funny thing called eta sitting in here. Okay? Now, I discovered that I got one force by coupling the particle to a one-index tensor, the A mu. I want to look at the next force. Well, the obvious thing is to couple it to a two-index tensor. Okay? But there's one sitting there already. Okay? So why don't we just change this guy? And that's all gravity is. Okay, so gravity is just this eta mu nu changes to g mu nu, which is a function of x. Okay, and that's gravity. So already in the point particle action, there's a suggestion as to how to couple the particle to gravity. You've got to make this guy eta mu nu depend on x. And this g mu nu is the thing you use to measure lengths in space-time. And that's all gravity is the field theory for g mu nu. So let's understand this. To understand it, we want to think of eta mu nu as corresponding to a special case of a matrix we're going to use to measure lengths in space-time. And the difference is that this g mu nu is going to be allowed to depend on x. It'll be different in different places in space-time, whereas the eta was a constant matrix. Okay? Remember, this eta is intimately related to Lorentz transformations. So this was invariant under Lorentz transformations. And what that means is that eta gamma delta is eta alpha beta lambda alpha gamma lambda beta delta, for example. Okay, we had this equation. What are the transformations? Well, what are these lambda gamma delta? Well, lambda alpha delta. Remember, the way they're defined is they are the coordinate transformations. Gamma x gamma. Okay? So these lambdas parameterize the coordinate transformations. So obviously it's true that the coordinate transformation matrix, so the coordinate transformation matrix and by that I mean the partial derivatives, dx prime alpha dx beta is lambda alpha beta. Okay, so special relativity is just a theory of these transformations from x to x prime, where they satisfy this equation. The partial, so x prime is this function of x, and the partial derivative of x prime with respect to x is a constant matrix. And so that suggests, generalizing this, when I make eta go over to G, it suggests generalizing the symmetry will generalize, or Lorentz symmetry generalizes to x, x alpha goes to x prime alpha of x, where this is any coordinate transformation. Okay, so that is called a general coordinate transformation, and Lorentz transformations are just the special case where those transformations are linear in X. There's another symmetry we talked about. Another symmetry we have used, another symmetry we have used is the symmetry under translations in space-time. X mu goes to X prime mu is X mu plus A mu, with A mu a constant. Okay, together, Lorentz transformations and spacetime translations form the Poincare group. Okay, so the set of all Lorentz transformations, i.e. constant matrices satisfying this condition, and translations form the Poincare group. By the way, what is the dimension of these groups? How many independent transformations are there among all of these? So how many, and when I say independent, I need to do something linear, okay? So what I mean by infinitesimal transformations, how many small transformations here are there which are linearly independent? So of course there are 3 rotations, okay? You can rotate about 3 independent axes. And how many boosts? 3 boosts, okay? So this is a 6-parameter group. Another way to get that is to say, obviously, lambda is a 4x4 matrix, so there are 16 parameters in lambda. But here I have 10 equations for the lambda, because this equation involves, is a symmetric tensor in 2 indices. So 4 times 3 over 2, 4 times 3 over 2, that will give the off-diagonal elements. There'll be 6 off-diagonal elements in this equation and 4 diagonal elements. So there are 10 equations for 16 quantities. So there are 6 linearly independent Lorentz transformations. And here I have 4 more. Okay, so this is a 10-parameter group. In fact, these are the most general continuous transformations. Continuous means they have a parameter which varies from 0 to other values. These are the most general continuous transformations. X alpha goes to X prime alpha of X, which satisfy, let's say it this way, which preserve eta mu nu, i.e., for which eta gamma delta is equal to eta alpha beta dx prime alpha dx prime beta dx gamma dx delta. Okay, so you can actually prove that if I insist on leaving eta invariant, but I allow my coordinates to change by any function, x prime of x, then the most general possibility for that function is are the Poincare transformations. So let me prove that, because the proof is not difficult, but it's tricky. It's sort of, and it'll give you a flavor of the other tricky things we do. So the proof is a nice little bit of practice with tensor algebra. So the proof. So I just take this equation, okay? Eta is a constant matrix, and I differentiate it with respect to x epsilon. D by dx epsilon. Okay? Just apply d by dx epsilon to both sides of the equation. On the left-hand side, I get 0. And on the right-hand side, I get eta alpha beta. Now I'm going to get a tired hand because there's lots of junk to write down. Dx epsilon dx prime beta dx delta plus eta alpha beta dx prime alpha dx gamma d2 x prime beta dx delta dx epsilon. Right, correct? I just take the second derivative, so I obviously get two terms, d by the epsilon of this guy, d by the epsilon of that guy. Those are my two terms. Now we do something entertaining, which at first sight looks pointless, but this is the cleverness. You say, well, I have this one equation. What can I do with it? Well, of course, you can change around the indices and add it to itself. Okay, that sounds silly, but as you see, it really works. So we'll take the same equation and add to it the equation with gamma replaced by epsilon, and vice versa. It's still a valid equation. Now this does nothing at all, right? So this looks thoroughly pointless, but let me do it anyway. I'm going to add it, the same equation. This was done by 19th century mathematicians, and they were like totally brilliant at seeing all kinds of clever tricks. Okay, so now I've got to replace gamma with epsilon. Okay. What?
You're not replacing the first gamma.
Did I get something wrong?
No, I'm just asking whether you're not replacing the first gamma. You're only replacing the gamma in second.
Oh, these are equal, right? Partial derivatives commute.
Oh,
so
you're also replacing epsilon with gamma. Okay.
Yeah, epsilon with gamma. So this is d by dx epsilon, d by dx gamma, but those derivatives commute. So it's actually the same thing. Okay, so now we've got the x prime alpha dx epsilon. So here I get something a bit more interesting. It's still pretty mind-numbing, but dx gamma. And now we're going to subtract from this the same equation, but with epsilon replaced by delta. Okay, so basically this equation had three free indices, gamma, epsilon, and delta. And you're free to write it down and replace any of those by any of the others, any one of the others. And so now I'm going to get minus eta alpha beta d2 x prime alpha dx gamma dx delta dx prime beta dx epsilon minus eta alpha beta dx prime gamma okay. So I've written down a lot of stuff. And now we notice that the very nice things happen. You see, this term is precisely that term. Okay, so this one cancels that one. Okay, This term is precisely, do I mean that term? Should be this one. Yes, it's exactly this one. Okay? Because this term and this term have just relabeled alpha and beta. Right? So x prime alpha goes to x prime beta goes to x prime alpha, eta alpha beta is symmetric. So these two cancel. Okay? And these two, as we already noticed, are identical. Okay? So what this proves is that eta alpha beta d2 x prime alpha dx gamma dx epsilon dx prime beta dx delta is 0. Now that's an interesting equation because eta is an invertible matrix, and this is also an invertible matrix. By the way, this is the definition, the definition of a good coordinate transformation, a non-singular coordinate transformation, is that the coordinate transformation matrix should be invertible. It means you can basically go back and forth between the two coordinates locally. Okay? So this is invertible. This is invertible. And so you can just multiply by their inverses. And this proves that d2x prime alpha dx gamma dx epsilon equals 0. And this equation we can solve. Because this equation implies that x prime alpha equals lambda alpha, dx prime alpha dx epsilon is a constant, because d by dx is 0 with respect to any of t, x, y, z. Okay, so this must be a constant matrix. And this I can solve, because the derivative with respect to epsilon of this guy is a constant. So this implies that x prime alpha is lambda alpha epsilon x epsilon plus a alpha, where, so this is with lambda alpha epsilon equals constant, and with a alpha equals constant. Okay, and voila, that's a Poincare transformation. So it's rather neat that once you fix the metric of space-time to be eta mu nu, the only coordinate transformations which preserve the metric are the Poincare transformations. Now, it sort of begs the question, is the metric of space-time eta mu nu? Okay? And of course, the answer is it is not. We live in a metric which is more like de Sitter space, where our universe is dominated by dark energy. It's expanding exponentially. But Minkowski is a pretty good approximation. Okay, locally, for short times and short distances, it's a very good approximation to take the metric to be eta mu nu. And so the entire set of symmetries of our part of the universe are these guys. The entire set of space-time symmetries are these guys, and all the consequences of that follow. Okay, any other questions, quick questions? Yeah. Or not quick questions.
Does the Poincare group span all the possible linear?
Yes. Yes, I already, well, I've just proven it.
Okay.
That is the proof. It doesn't, in fact, doesn't depend on linear. Nothing in this argument said it had to be linear.
Yeah.
This was not an infinitesimal proof. This is actually a global proof. Mm-hmm. I never had anything infinitesimal. So the most general large transformation is of this form.
Okay.
Let me, while I'm at it, because I can't shut up, let me just mention, you see, the way I've argued it, Maxwell's theory had everything in it implicitly, right? It had relativity, special relativity. It had E equals mc squared. Everything was there. But it was hidden in the symmetries of the theory. The theory had symmetries between space and time, electric and magnetic fields, charges and currents. All these symmetries were implicit in the theory. In fact, Maxwell's theory had a lot more symmetry. Okay? Can anyone tell me another symmetry Maxwell's theory had? What was the driving idea behind particle physics throughout the 20th century, right? Gauge symmetry. Maxwell theory has gauge symmetry. Okay? So gauge symmetry was already there. What is gauge symmetry? Gauge symmetry is the statement that if I write the field strength, right, and if I replace A mu by A mu prime, which is A mu plus the gradient of any function, the field strength doesn't change. And as we've seen, the action doesn't change because the action only depends on the field strength. So this is a symmetry of the Maxwell action. It's gauge symmetry, and that idea was the basis for all of particle physics, that the electroweak theory is a gauge theory, the strong theory is a gauge theory, their actions are just f squared, okay? Particles coupled to them according to that law. It's all there in Maxwell, okay? So just a slight difference, which is that these other theories have some indices on the gauge potential, and there are some indices on these gauge parameters. So, you know, it's all there in Maxwell. Okay. The gauge group slightly changed. It was U1 in Maxwell. It became SU3 times SU2 times U1. But honestly, Maxwell deserves all the credit for those theories. Now, there's actually yet another symmetry in Maxwell's theory. Do you know what that is? This is a symmetry which I believe is going to change physics in the future. It hasn't yet, but it looks that way.
Well, there's no sources to scale invariance.
Pardon?
There's no sources, then there's scale invariance.
No, just free Maxwell theory.
Yeah, so there'll be scale.
Scale invariance. Thank you. Yes, scale invariance. So Maxwell theory has another theory, which is if you change scale, if you do the transformation x prime mu equals lambda x mu, that's called a dilatation. I just stretch all the coordinates. Okay? Maxwell's theory is invariant under this transformation. In fact, that's not all, because this transformation is part of a bigger group called conformal transformations. And Maxwell's theory is invariant under conformal transformations. Okay? And there is increasing evidence that the universe, the laws governing the universe, are actually invariant under these conformal transformations. And again, they were there in Maxwell's theory, but we haven't quite learned how to implement them properly. So it's just amazing how Maxwell kind of opened the door to all of the really fundamental ideas in physics. By the way, this scale symmetry is responsible for the fact that a radio wave is the same as a light wave. It's just scaled, right? When we have waves, we have X-rays and gamma rays and radio waves and light waves. They're all exactly the same thing, just scaled. Okay. And that's a consequence of this dilatation symmetry. So personally, I believe a very attractive idea is that physics has no scale. There's no fundamental difference between space and time, nor is there any meaning to the statement that something is 1 meter long. That's a scale, right? Nor is there a Planck length. I mean, so many people believe there's a Planck length. String theorists believe there's a string length. Okay? In my opinion, a much more attractive idea is there's no length. Okay? And then you have to understand why it is that there appears to be lengths. And that's because the symmetry, this dilatation symmetry, is broken. And there are physical mechanisms through which scale symmetry can be broken, and then it appears there's a length. And that seems to be a very interesting idea. So physics is not about kilograms, meters, seconds. It's got to be about something else. Maybe it's information, maybe it's entanglement. We don't yet know. But there shouldn't be any, I mean, one point of view is that there really shouldn't be any lengths, times, or masses in physics. Physics is about something else. Any other questions? Okay, I'll see you this afternoon.